Hi, in this video we're going to do a problem from section 6.7, which is sufficient statistics, that is very similar to your homework problem. So I'm hoping that by walking through this example that it helps you solve the homework quicker and easier, and that it maybe sinks in a little bit better how to do this. All right, so we have a random sample from the normal distribution where mu is equal to 0 and the variance, so the mean is 0 and the variance is sigma squared. We want to find a sufficient statistic for sigma squared, not sigma, but sigma squared. And this is going to throw a little bit of a monkey wrench into what we do. But let me show you a technique to make this a lot less painful for us. Okay, so the first thing I need to do is I'm going to write the distribution of a normal random variable. I'm not going to plug in 0 for mu yet. I'm just going to write the general formula. So it's going to be 1 over sigma square root of 2 pi exp negative x minus mu quantity squared over 2 sigma squared. Now, I need everything in terms of sigma squared, not just sigma. So how can I make this sigma turn into sigma squared? Well, I can put it under a square root sign, so I can move it inside here. And that would do it because the square root of sigma squared is sigma. Okay, so that's what we're going to do. Whoops. So this is going to become 1 over square root of 2 pi sigma squared. exp, and now I'm going to plug in for mu equals 0. So it's going to be negative x squared over 2 sigma squared. Now I have this in the form of sigma squared everywhere. Why do I need this? Because when we're going to find the sufficient statistic and later the MLE, we need to have everything in terms of the parameter that we're going to find. When we do the likelihood function, we're going to do L prime of sigma squared. That is d sigma squared of L of sigma squared, not d sigma. So this square is going to throw a little bit of a challenge our way. So I'm going to help you mitigate this challenge. We're going to let theta equal sigma squared. Now we'll solve our problem. We'll just have a theta instead of something squared in there. Then f of x is equal to 1 over square root of 2 pi theta exp negative x squared over 2 theta. Now, when we use this for our likelihood function in part B, it's going to be a lot easier to handle. Okay, so we might as well start from the start, but you don't have to. Okay, so the first method is the factorization theorem. Okay, and so I need to write this in terms of, I need to write the joint PDF first. So joint PDF of x1, x2, up to xn. And these are all supposed to be capital. Okay. So I've got f of x1, x2, up to xn is equal to the product of f of x. And I'm going to write this as 2 pi theta to the negative 1/2, okay? And then e to the negative x squared over 2 theta, okay? Since we don't have much in the exponent, we can do it without much problem. It's not too messy. So this will be 2 pi theta to the negative 1/2 e to the negative x squared over 2 theta. So the product of this constant 2 pi theta, there's no subscript in there. In fact, what I need to do is make sure that I put an x sub I, so that minus x sub I quantity squared over 2 theta. That way, if we use the index I, then it's clear that everything without the index doesn't depend on it. So it's just a constant. So this is going to be 2 pi theta to the negative 1/2 times 2 pi theta to the negative 1/2, and we do that n times. And so we're going to have 2 pi theta to the negative 1/2 n times. So that's going to be to the nth power. And then we're going to do e to the negative x1 squared over 2 theta, e to the negative x2 squared over 2 theta, and so forth, e to the negative xn squared over 2 theta. And so we add the exponents, negative x1 squared over 2 theta minus x2 squared over 2 theta minus negative x sub n squared over 2 theta. And so we're going to have negative sum of xi squared over 2 theta, common denominator. So we're going to have e to the negative sum of xi squared over 2 theta. And that is our joint PDF. So let me get rid of the extra scribbling here. My scratch paper. When you have a whiteboard-like object, it's easy to do that and then erase it. When you're using ink or lead and paper, it's a little different. So, all right. Now, for the factorization theorem, I need h that's a function of x only. This, and I haven't simplified this. So let's do that. This is equal to 2 pi theta to the negative n over 2 e to the negative sum of xi squared over 2 theta. Okay. Now, this, nope, too much. This is going to be my h of x1 up to xn. There is no x in here, so we could say that this is equal to 2 pi theta to the negative n over 2 times xi, let me do this. x1 to the 0, x2 to the 0, up to xn to the 0. And so that's 1 times 1 times 1 times 1. So we can write it as a function of x1, x2, xn. So that is h. And then this is a function of phi of u of x1 up to xn and theta. Okay? So now we see theta here. Oh, I'm sorry. I need to do something better than this. I have theta still over here. So I need to move theta out of this. Sorry, I need to rearrange my formula. This is going to be 2 pi negative n over 2. Then theta to the negative n over 2. Clean up a little bit more. Then I've got e to the negative sum of xi squared over 2 theta. Now this is phi of u x1 xn theta. And this is h of x. And we'll write it like that, meaning that it's a vector. Okay, so by the factorization theorem, u of x1 up to xn is equal to the sum of xi squared, so y equals this, the sum of xi squared, is a sufficient statistic for theta, which is equal to sigma squared. So that was method one, the factorization theorem. Well, we could also use the exponential family. So 2 exponential family of distributions. So that's method 2. And so we write f of x is equal to, and we have sigma. So we can go back to, we've already written this as an exponent, or we've written it as a simple form. So we have 2 pi to the negative 1/2, and then we have theta to the negative 1/2. I'm looking at this formula here, okay? And then we have e to the, actually, I'm going to combine these. There's no, yeah, I guess I can leave it like that. exp to the negative x squared over 2 theta. Now, I'm going to write this in exponent form. So I'm going to take e to the log of this stuff. And so this is going to be exp, and the first term is going to be log of 2 pi to the negative 1/2. And the second then plus log of theta to the negative 1/2, and then minus x squared over 2 theta. Okay. And so I can rewrite this as exp, and I've got negative x squared. So I can rewrite this, just to be precise, I can say that this is 1 over 2 theta times negative x, oh wait, no, I don't want to do that. I want to put the negative over here, times x squared. And then I have, then I can do, this is minus 1/2 log theta minus 1/2 log 2 pi. Okay. I'm pulling the exponents down. These negative 1/2 go in front of the log. And now that I have it in this form, this is k of x, this is p of theta, this is q of theta, and this is s of x. And again, this can be negative 1/2 log 2 pi x1 to the 0, x2 to the 0, up to xn to the 0, and all of these are 1. So that's why it's s of x. The constant works for s of x. And by the theorem for the exponential family of distributions, the sufficient statistic for theta equals sigma squared is the sum, we'll say y equals the sum of k of x equals the sum of x squared. Okay? And I can put x sub I here. It's fine. So both ways, we end up with y equals the sum of x sub I squared as the sufficient statistic. And this would be here for sigma squared, sum of xi squared. Now, part B, show that the MLE of sigma squared is a function of y. To do this, we first have to find the MLE of sigma squared. So I'm going to use f of xi equals, and I'm going to write it in the form of 2 pi to the negative 1/2 theta to the negative 1/2. So you'll notice that I'm letting theta equal sigma squared. Okay, so theta to the negative 1/2 exp to the negative x sub I squared over 2 theta. And then the joint distribution, or the likelihood function, I'll just go ahead and write it as the likelihood function of theta is equal to the product of f of xi theta, I equals 1 to n, which is equal to the product from I equals 1 to n of 2 pi negative 1/2 theta negative 1/2 exp negative x sub I squared over 2 theta. Okay? And this is equal to 2 pi to the negative n over 2 theta to the negative n over 2 exp to the negative sum of x sub I squared over 2 theta. Okay. Now, L of theta is equal to negative n over 2 log 2 pi minus n over 2 log of theta minus sum of xi squared over 2 theta. Now, I need to take the derivative of this with respect to theta. So again, taking the derivative with respect to theta is a lot easier than taking the derivative of sigma squared. Keeping the fact that it's sigma squared in mind and not trying to use the chain rule on it or the regular differentiation, 2 sigma, type of thing. That's difficult for me at least. So this is the way, making this substitution for theta equals sigma squared is the easiest way to do it. So when I have any power of something and that's going to be my parameter, I make a substitution so that I don't have to think as hard. Okay, so L prime of theta is going to be negative n over 2 times 1 over theta. I'm going to rewrite this. Negative n over 2 log 2 pi minus n over 2 log theta minus 1/2 theta to the negative 1 sum of xi squared. Okay, so I'm writing this with a negative exponent, so it's easier to differentiate. Okay, so this is minus 1/2 times negative 1 theta to the negative 2 sum of xi squared, which is equal to negative n theta to the negative 1 plus 1/2 theta to the negative 2 sum of xi squared. And then this could be equal to negative n theta over theta squared plus sum of xi squared over 2 theta squared. So somewhere I missed my 1/2. This is a negative n over 2. Yeah, so there's a 2. So negative n theta over 2 theta. Okay, good. And so this is equal to negative n theta plus sum of xi squared over 2 theta squared is equal to 0. And so this is true if negative n theta plus sum of xi squared equals 0. And that is only true if n theta is equal to the sum of xi squared, which is true if theta is equal to 1 over n sum of xi squared. So this is going to be our MLE, but we need to verify, check, that it is a maximum. So we need to take the derivative, L prime prime of theta, and I'm going to use this version, but I'm going to rewrite it. So this is d theta of, and now I'm going to say, actually, I want to write it which way? I want to write it, I'm going to use this one right here. Sorry, I'm going to use that one. I'm going to use this form here where it's using a negative exponent. So equals d theta of negative n over 2 theta to the negative 1 plus 1/2 theta to the negative 2 sum of xi squared, which is equal to positive n over 2 theta to the negative 2 minus 2 over 2 theta to the negative 3 sum of xi squared. Okay? So I need to find a common denominator, so I can rewrite this as n over 2 theta squared minus 2 sum of xi squared over 2 theta cubed. So you notice I didn't cancel the 2's there because I want a common denominator, and this has a 2 in it. So I'm leaving that 2 alone. So this is going to be n theta over 2 theta squared minus 2 sum of xi squared over 2 theta cubed. Now, I need to make a substitution for the sum of xi squared. And so I come up here and I find that the sum of xi squared is equal to n times theta. So n theta minus 2 times n theta over 2 theta cubed equals negative n theta over 2 theta cubed. So this is less than 0 for all theta. And I can simplify this so that it's even more clear. We know that theta is greater than 0, but this is equal to negative n over 2 theta squared. So that's less than 0 for all theta. Even though theta has to be positive anyway, the square is positive, 2 is positive, n is positive, so the negative of all this has to be a negative value. Okay? So for all theta, therefore, let's see, so therefore, theta equals 1 over sum of xi squared is a maximum point therefore L of theta, and thus L of theta. Therefore, theta hat MLE equals 1 over n sum of xi squared is the MLE of sigma squared. So actually, I'll rewrite this just to be clear that theta hat MLE equals sigma hat squared MLE. So that's the MLE of sigma squared. Now, is the we want to show that it's a function. Therefore, y equals the sum of xi squared equals n times sigma hat squared MLE is a 1-to-1 function of the MLE. Okay, so the MLE is a sufficient statistic. Oh, yeah, so I could say, so the MLE is a sufficient statistic for sigma squared. Okay, now I'm done. All right, is the MLE of sigma squared biased or unbiased? Now, here is how we do this. E of theta hat MLE equals E of sigma hat squared MLE is equal to E of 1 over n sum of xi squared, and do not, when we have the normal distribution, please do not go to the integral. In fact, if you can avoid the integral when you're doing this expectation or bias, then do so, if at all possible. So if you know the expected value and you know the variance, you should be able to avoid going to the integrals or the summations if it's a PDF, okay? A PMF, I'm sorry, if it's discrete. So what I can do is I can pull the constant out, and then remember that the expected value of the sum is the sum of the expected value. So how we figure this out is that sigma squared equals EX squared minus mu squared. EX squared equals sigma squared plus mu squared. I'm going to make that substitution. So this is equal to 1 over n sum of sigma squared plus mu squared equals 1 over n, and then I will have n times sigma squared plus mu squared. They're constants. They don't have any subscript I. And so this n and this n is going to cancel out, and this is going to be sigma squared plus mu squared. Oh crap, wait. Mu is equal to 0. Equals sigma squared. Therefore, the MLE of sigma squared is unbiased. And that is how you do the problem. Okay, so that's it for this problem. I hope this has walked you through how to do this, how to think about it a little bit more, and keep you from making a mess by going after, you don't want to use derivatives for these unbiased if at all possible. Use what you know about the distribution. Okay? If it's something to do with x, what's the mean? If it's something to do with x squared, what's the variance? Solve for e of x squared. And it usually works out pretty well. Okay? So we hope to see you next time. Take care.